Hello everyone, how are you here at NVIDIA GTC? That's the GPU Technology Conference in San Jose. I'm here with Rev Lebaredian. He's the VP of Omniverse and the simulation technology at NVIDIA. Hey Rev, nice to see you.
Very nice to be here with you.
We're going to talk a little bit more about physical AI today, but before we do that, why don't you introduce yourself and talk to us more about what exactly you do and what Omniverse is and what you do at NVIDIA.
I've been at NVIDIA for quite a while, for 23 years now. I came from the visual effects industry in Hollywood, where my specialty was computer graphics and specifically rendering for the purposes of creating images in movies. When I came to NVIDIA, I applied those same ideas, the same technologies to the world of real time so we can make interactive video games. Over the past 10 years or so, I've been busy applying the same technologies we used for video games to simulate virtual worlds in video games for the purposes of creating robots, and more specifically for building robot brains.
That's fascinating.
And so Omniverse is the platform, the technology platform, our operating system for simulating the real world, but simulating it in a computer so that we can produce AIs trained from inside those simulations and tested inside those simulations so that we can be certain that they're going to behave well when they come out into the real world.
That's awesome. Really the convergence of the physical and virtual world. Yeah, awesome.
Yes, the first applications of AI that we've seen is largely in the realm of thought, abstract things that we can just create in our brains, information. We applied it to text and we applied it to some imagery, the stuff that's already naturally digitized inside, available on the internet. But where we believe the most value of AI is going to be realized is out in the physical world, in our world of atoms. And so in order to produce those AIs, we have to take the rules of the physical world and represent it inside a computer so that we can simulate these worlds, these virtual worlds, and create a playground for our AIs to learn and for our AIs to be tested.
Speaking of that, how does NVIDIA's concept of physical AIs differ from the traditional large language models or the image generation models?
I don't know if they specifically differ. It's actually sort of like an additional thing that we're thinking of. So an LLM it's in the name itself. It's a large language model. A foundation model that understands language, understands the rules of language, the patterns inside language. A world foundation model is one that is essentially the same thing. It understands the rules, but the rules of the world, the physical world around us. Now we've seen a lot of these video generation models come about in the course of the past year. Largely these models are about generating worlds, but they haven't been focused on generating physically accurate worlds. The job of creating a video for the purposes of entertainment is very different than the job of simulating a world so that it matches the actual world exactly. You see this all the time in traditional simulation. Game engines and the simulations we use to create the effects inside movies are very different than the simulators that we use to design our products, to design cars or airplane wings. There's a different level of rigor. So what we're focused on with the world foundation models we're building is this physical accuracy, and for the purposes of creating AIs that can be used inside robots that operate inside the physical world. So it's really critical for us that they're not trained on things that are not real. We don't want them learning from cartoons.
Yeah.
We don't want them learning from fake physics that you might see in a fantasy video game. They need to learn from the actual world and match the world exactly.
That makes sense to me. Yeah, maybe just say, hey, Rev, during Jensen's keynote, he made many exciting announcements related to physical AI. Can you share a little bit more with those who are not at the keynote?
Yes, there's too many announcements to list all of them here, but some of the ones that are important to me and top of mind for me, there were many announcements about Cosmos.
Yeah.
We first announced Cosmos at CES, and we've been hard at work developing a lot more on top of that. So we're releasing 3 sets of new models within the Cosmos framework. There's Cosmos Transfer, which can take as input the output of classical simulators like Omniverse, and layer on top of that sort of the last mile of simulation to make it really, really real. We have Cosmos Reasons, which can take as input information about a world and extract insight from it, much in the same way we use LLMs like ChatGPT. You can give it a whole bunch of information in a large document and ask it to summarize it for you.
Okay.
We can do the same thing with Cosmos Reason. And then we also have Cosmos Predict, which is about predicting the future. So when you give Cosmos a world in a given state, in a given point in time, it will predict what is about to happen, what's going to happen in the next bit of time.
Crystal ball, right?
It's kind of a crystal ball, which is really what physics simulations and understanding the laws of physics is all about. If you know them well enough, you can kind of predict what's about to happen.
Yeah.
When you throw a ball in the air,
The gravity.
given what its current position is and its velocity, we try to predict what's going to happen next. It's something natural that we do in our brains without even thinking about it. When you see somebody throw a ball, you can kind of predict where that ball is going to be so you can go catch it.
Yeah.
So we have a set of models about predicting the future as well as part of the suite. We also are continuing to open source our suite of tools for creating Cosmos and these kinds of World Foundation models, along with all these models being open weights, so that anybody can use them for any purpose, and they can also use them as a starting point to build their own World Foundation models.
That generates so much more efficiency, as you know, right? So that's exciting. Thank you. What are the 3 categories of the physical, the robots, right? The distinct categories of robots related to physical AI?
Yeah, the way we look at it, we categorize robots into sort of 3 areas. The first is facilities.
Okay.
Buildings themselves can be a robot, because even though most people wouldn't think of a building as a robot, if you bring a robot down to its essence, all a robot really is a agent of some sort that has three things that it does. It perceives, so through sensors or inputs, it makes an understanding of the world, and then it reasons. There's cognition. It makes a decision based on what it perceives to do something, and actuation, which is how the agent can manipulate things inside the world.
Okay.
So a building can do this by placing sensors in it. You have cameras, you have temperature sensors, you have
Maybe
the
natural disaster, right? Sensor.
All kinds of sensors. But even in just any normal building, there's security cameras, for example, right?
Yeah.
Those are sensors, and it's watching what's going on inside the building. We have important buildings in industry like factories and warehouses, and so we place sensors inside these to watch what's going on. So the building itself if we give it an AI, physical AI, connect those sensors to that AI, it can reason about what's going on. Then it can make some decisions, like maybe giving access to a robot or a human to a certain area of the building, or changing the climate conditions in the building based on how many people are occupying a given area. And it can actuate. It can actually open doors. It can activate other robots, maybe activate conveyor systems, can change the temperature. So
without humans supervision.
That's right.
Yeah.
This is an autonomous agent.
Yeah.
The building itself becomes a kind of robot, an autonomous agent, where it's watching. It's inside itself. It has sensors to look inside and make decisions and activate things inside it. Another kind of robot is self-driving cars or self-driving vehicles. These are robots by the same definition. A self-driving car has to sense the environment. It perceives it, makes an understanding of where all the other cars are, how fast they're moving.
I
where the
tested
pedestrians-
one recently, by the way. It's really cool. Yeah.
Here in San Francisco?
Yeah.
It's really amazing.
Yeah.
They're everywhere.
Oh yeah.
And so it has to perceive the world, and then it makes a decision based on its goal of taking you from one location to the other, what the next action is. Should it accelerate? Should it steer? Should it brake? And then it does those things. And that's the actuation. It actually acts upon the world by braking or steering, sends a control signal, and some physical thing in the world is affected. And the final kind of robot is what we normally think of as robot, the robots. So these are humanoids or manipulator arms, these sorts of robots. These are broadly the classes we look at. That last one, the humanoid robots, we're the most excited about because this has been, a long time dream, largely in science fiction for forever, and in the last 20 or 30 years, there's been many attempts at humanoid robotics because if the dream is to be realized, the value it's going to unlock is very large.
Oh, yeah.
Being able to place a general purpose robot that could do many of the things a human would normally do, dull, mundane, repetitive things that a human might do, doing that at scale, placing it in the environments that we've already created for humans, that's going to unlock a lot of value in our factories, in our warehouses, in our retail stores, in hospitals, and so on. And so we think that time has come.
Absolutely, and especially with the great tsunami coming right around the corner, right? A lot of people being retired, we may be short of workers in these factories.
That's right. It's what you just said is extremely important for people to absorb. We have a demographic crisis worldwide that's happening. Populations are decreasing. We have less children being born, which means that over time, our capability, if we don't change anything in how we produce things, how we manufacture, we are going to have less capabilities. We're not going to be able to produce as much, which is a big problem for societies. If each generation is not producing more than the previous one, then things will start going downhill because our older people are dependent on the younger people producing more so that they can be taken care of when they're not producing.
Exactly. By the way, Jensen introduced this concept of three computer solution at CES keynote. I'm curious to hear from you, right? Could you explain or unpack that a little bit more, what that is and how that's relevant to physical AI?
Yes, this is a really important concept, and I'm glad you asked the question. When we talk about computers in relation to robots, typically people think of the computer that's inside the robot. So the computer that's inside the head or body of a humanoid robot.
Not because of movies, right?
Yes. Or you think of the computer that's in your self-driving car. You said you just rode in one. There's definitely computers in there doing essentially supercomputing tasks to perceive and operate in the world. That's a very important computer. That's a computer that we build. A lot of the robots out there, most of them, and most advanced cars with advanced computers in there are using NVIDIA computers. But that's kind of the last computer in the pipeline. Before you get to the point where you have a computer in the robot that's running the software that's effectively the brain of the robot, you have to create that software. You have to create that brain. So before you get there, you first need a supercomputer that's going to generate the software, the neural networks, the AI, the model that's going to be placed in there. And so for that, you need an AI computer. That's our DGX computers, the ones that NVIDIA is known for now, that everybody's
powered at 384 out of 500 supercomputers.
In the top 500 list, but almost every AI that's created out there is being done on our computers. And so that's the AI computer stack. But there's a third computer as well that I don't think most people quite understand or even see, but it's just as important, which is the simulation computer. We call it the omniverse computer, or OVX is the hardware, reference hardware platform that we create. This is a computer that simulates the physical world so that we can generate the data that feeds into the AI computer that will create the physical AI intelligence that is then sent to the computer that's in the robot. So you need all three computers working together. You need the simulation computer to create the data. You need the AI computer to convert the data into intelligence. And then you need the robot computer in order to take that intelligence and use it, run it in the real world. There's a second use for that simulation computer as well that's also part of creating the robot, which is once you've created the brain in the AI computer, before you actually send it to the real world, before you send the brain into your self-driving car or into the humanoid that's working in your factory, you would like to test it. You want to make sure that it's going to behave well, that there aren't going to be any regressions back, any bugs that are introduced where it behaves badly, because we're continually updating them, making them smarter and smarter. But you want to make sure that they're good, and you don't want to test them out in the field. You don't want to endanger any humans on the roads or inside a factory. So the place where you're going to test them is in the simulation computer. So you use the simulation computer to generate the data, to create the AI from the AI factory, from the AI computer. And then you take that right back into the simulation computer to test it. And then once you feel good, you've driven your self-driving car billions of miles, or you've run your robot in a virtual factory for millions of hours.
You then put it in the real world.
Then you can say, all right, now this is safe. Let's take this AI and place it in the real robot. And now we're confident it's going to work.
That's a really vivid description, right? Thank you. Well, let's switch gear a little bit, talking about synthetic data. Why is it so critical for perfecting AI models, especially in robotics and autonomous vehicles?
Well, as I think everybody understands these days, the critical input, the critical thing that we need to create AI is lots of data. And it's not only important to have lots of data, but you need lots of the right data that has coverage of all of these scenarios, all of the types of things we would like it to understand. With large language models for text, we are fortunate in that text and language itself is a natural thing to have in digital form. So we already had the internet for decades. By the time we invented the transformer model and large language models started to appear. So we could go mine the internet for all of this text, all the digital stuff to create GPT and Claude and Gemini and these amazing language models. But we want to take the same technology and extend it to the world, to the physical world. Unfortunately, the data that we need that describes the physical world isn't readily available in the same way text is available to us on the internet. You can't just go get it. The closest thing we have to information about the physical world on the internet is video.
Yeah.
We have some videos, lots of videos of things happening in the world, but the coverage of the things that we need is not in those videos. For example, there aren't a lot of videos about the intricate operations of a factory that produces electronics or surgery, heart surgery. There's just a limit of
data.
Yeah, and even that, the video data on its own is maybe not sufficient. We want to have more information about the actual state of all of the things happening that you would have to have special sensors for to gather.
Makes sense. Yeah.
So the best way to create that data, the best way to get that, is by first taking the world and placing it inside a computer in a simulation. And once we have a simulation, then essentially we have an unlimited source of data. If you think about all of the data on the internet as a sort of fossil fuel, like there's a limited amount of it that you can go extract, simulators, synthetic data generators, are essentially an unlimited renewable source of data. And so this is a key element that we have to have in order to produce physical AI.
Yeah,
We're not fortunate enough to have all the data that we need in order to create physical AIs readily available.
You're right. That might be one of the most important elements, right? So, Rob, I can talk to you for another hour, but in essence of the time, let's start. It's just my last question, right? Looking ahead, what are you most excited about the innovation in the next few years related to physical AI?
Well, I believe we're just at the beginning of this. We're sort of like, with the large language models, we're at the equivalent of the GPT-1 era.
Yeah.
It wasn't until GPT-3 where the world got to taste it or try it with ChatGPT was using a GPT-3.
Yeah.
And we've progressed a lot since then. And so I'm really looking forward to seeing what's going to happen in the next year or two. I think we're rapidly going to get to these next few levels.
Awesome. Thank you so much, Rev. I've learned so much from you today. I'm sure our audience will be thrilled about hearing what you have to say about physical AI. And I look forward to listening to your session at GTC, and I'll hopefully to see you around. Okay, thank you so much.
Thank you so much.